This is part 3 of chapter 22, section 2, and we'll be focusing on alkynes. So alkynes are hydrocarbons with triple covalent bonds. Like the double bond of alkenes, the triple bond of alkynes requires that the simplest alkyne have 2 carbon atoms. So alkynes are hydrocarbons with triple covalent bonds here, and then there will be enough hydrogen atoms for each carbon atom to make each of the carbon atoms happy. So in this case, there's only one hydrogen atom for each carbon atom because every carbon atom needs 4 bonds. And so the general formula for the alkynes is CnH2n-2. Alkynes have 4 fewer hydrogen atoms than the corresponding alkanes and 2 fewer hydrogen atoms than the corresponding alkenes. The simplest alkyne is ethine, and it's more commonly known as acetylene. So here we have ethane. This is an alkane, and we see that it has a molecular formula of C2H6, which corresponds to the general formula for alkenes, which is CnH2n plus 2. This is exactly what we have here. And then for alkenes, the general formula is CnH2n, and again, ethene, the formula for ethene corresponds to the general formula. And also note the endings ane for alkane, ene for alkene, and ethyne for alkyne. This is an alkane. They have only single bonds. Alkenes here have at least one double bond, and alkynes, this one has at least one triple bond. Now let's go to systematic naming of alkynes. Alkyne nomenclature is almost the same as alkene nomenclature. The only difference is that the ene suffix of the corresponding alkene is replaced with "-ine". A complete list of rules follows. Alkyne nomenclature use the rules for alkene nomenclature listed earlier in this section with the following exceptions. Number 1, name the parent hydrocarbon, locate the longest continuous chain that contains the triple bonds. If there is only one triple bond, add the suffix "-ine". If there is more than one triple bond, modify the suffix, for example, 2-adyeine, 3-atriine, and so on. Second, add the names of the alkyl groups. 3, number the carbon atoms in the parent hydrocarbon. Number the carbon atoms in the chain so that the first carbon atom in the triple bond nearest the end of the chain has the lowest number. 4, insert position numbers. Place the position numbers of the triple bond immediately before the name of the parent hydrocarbon alkyne. Place alkyl group position numbers immediately before the name of the corresponding alkyl groups. And finally, punctuate the name. So 2 examples of correctly named alkynes are given below. Here we have 1, pentyne. It's pentyne because there are 5 carbon atoms, and "-ine" because it's an alkyne since it has at least one triple bond. And the number 1 is here is because if we were to number this hydrocarbon, which is the parent hydrocarbon orality, from right to left, this hydrocarbon would bear the number 1. This is 3-methyl-1-butyne, and now let's break this name down. So the parent hydrocarbon would be this chain right here. It has 4 carbon atoms, therefore butyne, and "-ine" is for the single triple bond. 1, because again, if we were to number the parent hydrocarbon, in this case from left to right, this hydrocarbon right here would have number 1, so that's where the 1 comes from. And then methyl is the alkyl group that is on the third component of the parent hydrocarbon. Now let's look at properties and uses of alkynes. alkynes are non-polar. So like I already mentioned in the previous videos, almost all hydrocarbons are non-polar. So alkynes, like most other hydrocarbons, are non-polar and exhibit the same trends in boiling points and physical states as other hydrocarbons. So again, like going back to that chart, the larger the molecule of the hydrocarbon, the stronger the London dispersion forces. So the closer the atoms are, and so the boiling point is higher, and the more like solid the hydrocarbon is at room temperature. So the smallest alkyne, ethine, is a gas. That's not surprising given what I just said. And the combustion of ethine when it is mixed with pure oxygen produces the intense heat of welding torches, as shown in figure 2.11. As mentioned, the common name of ethine is acetylene, so these welding torches are commonly called oxyacetylene torches. So figure 2.11 says that ethine is the fuel used in oxyacetylene torches. Oxyacetylene torches can reach temperatures of over 3,000 degrees Celsius. So we're done with alkynes, and there's one last type of hydrocarbon that we'll look at, and it's the aromatic hydrocarbons. They are hydrocarbons that have 6-membered carbon rings and delocalized electrons. Benzene is the primary aromatic hydrocarbon. The molecular formula of benzene is C6H6. One possible structural formula is a 6-carbon atom ring with 3 double bonds. Okay, so here we have the basic structure of benzene. However, benzene does not behave chemically like an alkene. So this is important to note. Benzene does not behave chemically like an alkene. First of all, why are we talking about alkenes? We're talking about alkenes because if you noticed, this molecular formula of benzene resembles the general formula for alkenes, which is CnH2n. This is important to note because we might think that benzene will behave like an alkene because it has these double bonds, but despite this fact, it does not behave chemically like an alkene. The entire molecule lies in the same plane, as shown in figure 2.12, but benzene contains resonance hybrid bonds, and the structure of the benzene ring allows electrons to be spread through delocalized p orbitals over the whole ring. The structural and skeletal formulas below show benzene as a resonance hybrid representing the delocalization of electrons. So let's go to figure 2.12. Aromatic hydrocarbons. Electron orbitals in benzene overlap to form continuous p orbitals and allow the delocalized electrons to spread uniformly over the entire ring. So every atom has an electron cloud, and these electron clouds have these orbitals, and the p orbital looks like a dumbbell, something like this, and since there are many of them for each carbon atom, and imagine that there are many dumbbells, and they're not this small, so they will overlap, and this overlap will cause these orbitals to become one continuous orbital through which electrons will be able to travel from one atom to another, and this is what causes the delocalization of electrons in the benzene ring. So it's a important property of benzene. Okay, now aromatic hydrocarbons can be thought of as derivatives of benzene. So benzene is like the parent of all aromatic hydrocarbons. the simplest aromatic hydrocarbons have one benzene ring, as shown in the following example. So for example, this over here, methylbenzene is it's an aromatic hydrocarbon and it has one benzene ring. Let's answer this check for understanding question. How does the circle in the middle of the benzene ring better represent the type of bonding in benzene? So these double bonds, they don't disappear, they're just like combined into this circle in the middle. And we're asked about the advantage of this ring, like how does it better represent the type of bonding. So think about it, and then we'll go over the answer. This circle in the middle, it emphasizes the delocalization of electrons. So as I explained in the image above here, the orbitals overlap and form a continuous cloud, a continuous orbital. And it's a defining feature of a benzene molecule. And we finally got to the formative assessment. Yay. Okay, number 1, we're asked to list the basic structural features that characterize each of the following hydrocarbons. We talked about 4 different hydrocarbons in this section. There are alkenes, alkenes, alkynes, and aromatic hydrocarbons. Alkanes have only single bonds. So only sigma bonds. Also, out of all of them, they have the maximum possible number of hydrogen atoms. Another thing that I want to write down for every type of hydrocarbon is the general formula for each of them. So the general formula for alkenes will be CnH2n plus 2. Now alkenes, they must have at least one double bond. So at least one pi bond. And the general formula for it will be CnH2n. So minus 2 hydrogens from alkanes. Alkynes must have at least one triple bond. And its general formula is CnH2n minus 2. Again, minus 2 hydrogen atoms, and aromatic hydrocarbons, they are rings that have 6 carbon atoms. So 6-membered carbon atom rings. Another important feature of aromatic hydrocarbons is delocalization of electrons. That's when the p orbitals of each individual carbon atom merge. In number 2, we're asked to draw all of the condensed structural formulas that can represent C5H12. And then number 3 asks us to give a systematic name for each of the compounds that we'll draw in number 2. First of all, take a look at the molecular formula. It's C5H12, so it follows the general formula of CnH2n plus 2. This means that we're dealing with an alkane. So if we're dealing with an alkane, all of the bonds in the compound will be single bonds. From here, we can start drawing. For the first one, let's have all of the carbon atoms in a continuous chain, and then we'll add hydrogen atoms to each of the carbon atoms until they become happy. Each of the carbon atoms need 4 covalent bonds. And there we have it. It's called pentane. Ane because it's an alkane, and pent for the 5 carbon atoms. Okay, another structural formula that we can go with, it would be an isomer of pentane. We'll have 4 carbon atoms in the middle, and then we can have 1 branching down. And then we'll start filling them with hydrogen atoms again. And then we must not forget this one on the bottom. And ta-da! This one will be called, think about it. To make it easier to name it, we can redraw it a little bit to make it easier for our eyes to process it. So this is CH3, and then it's bonded to a CH, a CH2, and a CH3. And this over here is another methyl group. Okay, now it's easier to name. This compound, we have a parent hydrocarbon over here with 4 carbon atoms. So knowing that it's an alkane and that it has 4 carbon atoms, the last part of the name will be butane. And then there's 1 alkyl group, which is a methyl group. So we'll go here, and there's only 1 methyl group, so no prefix at the beginning. So far we have methyl butane, and numbering it, we get a 2 for methyl. So 2-methyl butane. Another common name for this compound is isopentane. Iso tends to stand for a common isomer of the more like regular, normal compound. And now a final way of drawing C5H12 would be having 3 carbon atoms in the middle, and then 2 will be going off to the sides. And once again, the hydrogen filling. Again, we can redraw it in a more condensed form. So CH3 on the side, and then a single carbon atom in the middle, and then we have more and more methyl groups surrounding it. Now let's name this compound. We have, well, the parent hydrocarbon could be either this or that, no difference. Either way, the parent hydrocarbon will have 3 carbon atoms, which will give the prefix of prop. And then ane will come from the fact that we're dealing with an alkene again. Now we have 2 alkyl groups, and they're both methyl groups. Since there are 2 of them, it'll be dimethyl propane. And then numbering it to 3. Again, it doesn't matter from which side we number. We have the number 2, and we'll have 2 2s because there are 2 methyl groups that are both attached to the second component. So the final name is 2,2-dimethylpropane. Now, number 4 asks us to give examples of a property or use of 3 hydrocarbons. Let's recall everything that we covered in this section and start with isomers. The more carbon atoms there are, the more structural isomers there are. Just like in this example with 2 and 3. The formula had 5 carbon atoms, and there are already 3 isomers for this molecular formula. The second property that hydrocarbons have is that the greater their molecular mass is, the stronger the forces, the intermolecular forces they'll have, and so it'll be more difficult to break the compound apart, like the individual atoms, and so their boiling points will be higher, and that's why they'll likely be more solid at room temperature rather than a gas or a liquid. And the final property of almost all hydrocarbons is that most of them are flammable. Just like ethine, which is used in oxyacetylene torches and can heat up to over 3,000 degrees Celsius. Now, number 5. We are asked to name the following compounds, and right away we can see that 5A, this is an alkane because there are only single bonds, and let's identify the parent hydrocarbon. It'll be this chain of hydrocarbons over here because it has the most alkyl groups attached to it, and it's the longest continuous chain. So this parent hydrocarbon has 6 carbons, so we'll call it hexane, ane for alkane. The 2 alkyl groups are methyl groups, so dimethyl will go to the front, and let's number the parent hydrocarbon now. 5 and 6. The 2 alkyl groups can be found on the second and the third item in the parent hydrocarbon, so 2,3 dimethylhexane. 5B. This is an alkene because there are double bonds. Since there are 2 double bonds, the ending will change to adian instead of ene. And there are 4 carbon atoms in the chain, so it's butadiene. It doesn't matter from which side we number the hydrocarbon. Either way, the bonds will be at 1 and 4. So 5B is 1, 4 butadiene. 5C, this one is an alkyne because there's a triple bond. So the ending will be -ine, since there's only 1 triple bond, and the prefix would be pent because there are 5 carbon atoms. So pentyne. And we'll number it from left to right because the triple bond is closer to the left. And we'll have the number 2 at the front. So 2-pentyne. Finally, number 6. Critical thinking, analyzing information. We have to write the structural formulas for an alkane, an alkene, and an alkyne that have 5 carbon atoms each. Why are these 3 hydrocarbons not considered isomers? So this reminds me of number 2 and 3, because again we're asked to write structural formulas for with 5 carbon atoms, but this time we're not limited to alkanes. We have to write the structural formulas for all 3 types of hydrocarbons. The simplest way to draw an alkane is to have the 5 carbon atoms in a straight chain in the middle, like this. And remember, alkanes have only single bonds, and they have enough hydrogen atoms attached to themselves for each of the carbon atoms to be happy. This alkane will be called pentane. Now, an alkene must have at least one double bond. Again, let's have our carbon atoms in the middle, and I'll choose to have the double bond between the second and third carbon atoms, but this double bond could be placed elsewhere, like here or here. It's just that the name would alter slightly. So instead of pentene, 2-pentene, it would be 1-pentene or 3-pentene. The number would change. And enough hydrogen atoms to make carbon atoms happy. And let's condense this structural formula a little bit. So this is a methyl group, then a CH group, a double bond, another CH group, then a CH2 group, and another CH3 group. So yeah, it's called 2-pentene. Now our alkyne must have at least one triple bond. And similarly, I'll have the triple bond between the second and third carbon atoms with enough hydrogen atoms. This shouldn't be here. Yep, and so this triple bond could be in between other carbon atoms, but again, the name would change slightly. So instead of 2-pentene, the number would change, indicating the position of the triple bond. So this is our alkyne. And the condensed structural formula would be a methyl group, and then 2 carbon atoms bonded with a triple bond, a CH2 group, and another methyl group in the end. Now, these hydrocarbons are not considered isomers of each other because their molecular formulas are different. So since this is an alkane, it corresponds to its molecular formula corresponds to the general formula for alkanes, which is CnH2n plus 2. It indeed has 5 carbon atoms, and so it has 12 hydrogen atoms. Our alkene also corresponds to the general formula for alkenes, which is CnH2n, so C5H10. And so does our alkyne. C5, the general formula is CnH2n minus 2, so H8. Isomers must have the same molecular formulas, but different structural formulas. But in our case, the 3 compounds do not have the same molecular formula, and these double and triple bonds account for the missing hydrogen atoms.